is our second. Right, we're recording the meeting. It will be available after Dr. Erica LaPlante's presentation today on YouTube. So look forward to that. Now, this is the second iteration, second talk within this webinar series. Before we had Dr. Chelsea Heverin talking about advances in biocements, and that was March 7th. Today, we're going to continue the spotlight on excellent research in advances of MgO-based cements, which I'm very, very excited to hear about. Now, our third speakers in this webinar series, Dr. Kinsey Skilling on optimizing sustainable concrete, unfortunately had to reschedule. And that's based on some of the work that he's doing that they're trying to patent. So hopefully the patents can come out soon enough so we can hear all about that exciting research. Now, before we get started with Dr. LaPlante's great information and talk, I wanted to remind everybody to register and definitely attend, submit abstracts to the 14th Advances in Cement-Based Materials. This is the premier conference on cement and concrete research, where scientific information is shared on the latest advancements of cementitious materials. So this year is going to be in Missouri S&T, Rolla, Missouri, June 19th through 21st, to the 21st of June. So highly encourage you to submit abstracts. They were due yesterday, but I believe those have been extended. So if you still have a keen interest in presenting, please do so and submit abstracts, right? So without further ado, let me introduce you to Dr. Erica LaPlante. She's an assistant professor in material science and engineering at the University of California, Davis. She obtained her PhD in earth and environmental sciences with a focus on geochemistry at the University of Illinois at Chicago, and her BS in geology from the University of Philippines. Dr. Erica LaPlante has produced peer-reviewed publications on mineral reactivity, the synthesis, durability, sustainability of cementitious materials, as well as the atomic structure controls and phase reactivity, low temperature mineral processing, and carbon dioxide sequestration. Most recently, Dr. Erica LaPlante received the NSF Career Award to discover pathways for the synthesis of cementitious magnesium silicate hydrates, which is part of the work that we're going to be hearing all about today. And she applies her expertise in the kinetics of low temperature aqueous processes at mineral fluid interfaces to address the many research questions in the fields of climate, sustainability, built environment, and energy. So very, very excited to welcome Dr. Erica LaPlante. And with that, the ground is all yours.
Thanks so much, JP, for that introduction. Let me share my screen. Oh, good slide. Okay. My screen okay?
Yep, looks great.
Okay, thanks so much. And thanks so much for having me here. My name is Erica LaPlante. Today, I'll be talking about kinetic studies of magnesium silicate hydrate precipitation and dissolution. The work I'll be presenting today are the latest work that came out from my lab. It's funded by the National Science Foundation. So motivation for this work is really the importance of infrastructure. Infrastructure has enabled our development by providing us with habitation structures, transportation structures like our roads, water, dams, and energy structures like our power plants. And if we think about the engineering materials that we use for this infrastructure, really concrete is a significant part of it. It's the largest manufactured product globally. Cement production, however, requires high energy and has a significant CO2 footprint. To look at CO2 emissions over time of different sectors, so coal, oil, gas, you can see cement is a sizable portion of this piece, of this total CO2 emissions that's in red. There's an opportunity here, however, because we use it at such large volumes that some improvements in this material could have high impact. So some of the research questions that we're answering in the lab is, could we improve the durability of this material? Could we partially replace ordinary Portland cement with something else to decrease the embodied CO2 emissions of the material? Or could we create new binder chemistries altogether? And in this talk, I will be focusing on this aspect of creating new binder chemistries in the form of magnesium-based cements. So I'd like to give an introduction of how concrete develops strength. So ordinary Portland cement, which is the cement that we use today, is composed of calcium silicates, aluminates, and ferrites. They're formed at very high temperatures in a kiln, about 400 to 1400 degrees C. So when they're at the room temperature in the presence of water, they're highly reactive. And the hydration of concrete, or hydration of cement and concrete, is characterized by a series of dissolution precipitation reactions. So here in this schematic, you have the cement grains, and you have the pore solution here represented in the blue. And what happens over time is the cement grains dissolve. That changes the composition of the pore solution, leading to supersaturation with respect to hydration products. And then you have the precipitation of these hydration products that then fill in the pores. So this, the important hydration product here is what we call CSH, or calcium silicate hydrate, and that is what's causing the increase in strength over time. So if we look at micrographs here of a cement paste, so this is at 3 days and at 28 days, the really bright areas here represent the unhydrated cement, the black areas represent the pore, and then the grayish areas represent the hydration products. So you can see that after a longer period of time in 28 days, there's less of the unhydrated cement and less of the pores, and then most of the cement base is composed of the hydration products, which is our CSH. During these reactions, the pH in the pore solution exceeds 12.5. And really the remarkable thing about this material is that all of this happens at ambient temperature and pressure. These equations here show the cement notation for the reaction of C3S. So this is just a cement notation that represents 3 units of calcium oxide and 1 unit of silicon dioxide reacting with water to form CSH, and then the other hydration products is what we call calcium hydroxide or Portlandite. So this idea of dissolution precipitation reaction has emerged a very long time ago. This Le Chatelier's model of cement hydration, which represents this dissolution of the anhydrous compounds as the first steps during cement hydration that then changes the pore solution composition. You have the precipitation of CSH and calcium hydroxide occurring after that, and then the dissolution of the anhydrous compounds continue, as well as the growth of the hydration products. So eventually you have, if you do reach complete reaction, then you'll have the hydration products in place of your anhydrous cement. So there's been model refinements on this over time, but fundamentally it remains a dissolution precipitation reaction. So the CSH is what we can consider as the glue in concrete. So look at the structure of CSH. It lacks long-range order. It's highly defected structure. The composition of this phase is variable, but it's generally accepted that the structure is composed of calcium oxide sheets that's sandwiched by silicate tetrahedra pairs and chains. So these green tetrahedra here represent your silicate tetrahedra, and then you have calcium ions and water that is found in between those chains. We also have the water occupying these interlayers. This micrograph here shows what a mature cement paste would look like, where we have this CSH showing this characteristic fibrillar structure. There's a significant influence of temperature as well as the pore solution composition on the final structure and the composition of this phase. So the focus of what we're doing right now is on magnesium silicate hydrates. So magnesium silicate hydrates would be the magnesium equivalent of CSH. It's naturally found. There's natural analogs of it in ultramafic rocks. These are rocks rich in iron and magnesium, as well as in concrete that is found in seawall, for example. So concrete that's been altered by seawater. If we look at the structure of MSH, it's also highly defected. It has a structure that could be akin to a serpentine or talc. So serpentine is composed of this magnesium octahedral layers and silicate tetrahedral layers, and it's alternating OT structure. And then talc would be a TOT structure where you have a tetrahedral, octahedral, and tetrahedral. And then you have this units repeating. And so MSH can be characterized by either of these two, but just with more defects, with a lot more defects. The hypothesis around the use of MSH is the characteristic of the magnesium ions compared to the calcium ions. So because of the greater barrier for water exchange around the magnesium ions, this suggests the greater stability of MSH cements compared to CSH cements. And that's also would be consistent with the greater degree of polymerization, silicate polymerization in MSH. It's where we have sheets instead of chains, as what we see for CSH. This is a micrograph here showing what an MSH might look like. And so it's showing these opportunities. However, there's still a lot of questions on the use of this MSH cement. It's not widely used right now. We still don't know a lot about the kinetics of its precipitation. How does it develop strength? So structural mechanisms for strengthening, and also the stability of this phase under conditions that's relevant for the application. So the first studies that we did is about the synthesis of MSH from aqueous solution. So we take a solution containing dissolved magnesium and silicon, and then we grew this MSH homogeneously or heterogeneously on a single crystal magnesium oxide substrate. We looked at the effects of temperature, magnesium silicon ratio, and time for different magnesium and silicon concentrations in a solution. The first thing we ever do when we do a synthesis like this is to do geochemical modeling. So this shows the saturation index as a function of the magnesium to silicon ratio of the solution. So saturation index gives the logarithm of the ratio of the ion activity products and the solubility products. So that means that positive values of saturation index means that there's a tendency for precipitation, and negative values of saturation index means a tendency for dissolution. So we can see here in the models is that there's high degrees of supersaturation with respect to MSH in all cases. The symbols here represent the measured values. We see a good correspondence between the measured values and the modeled values at low magnesium to silicon ratios. But however, at high magnesium silicon ratios, we see a divergence. You see here, it's evident from the pH. So we did another calculations in which we precipitate, we assume equilibrium with respect to brucite. And then we can see here that the magnesium silicate, that at high magnesium silicon ratios and the pH, we get a much better match between the measured and the calculated pH. So this modeling suggests that there's a rapid formation of brucite or MSH. So the precipitation of MSH would have the same effect at high magnesium to silicon ratios. So to understand the structures of this phase, we looked at infrared spectroscopy. Since MSH is a silicate mineral, we can characterize it by looking at the silicate species that's found in the solid. And for silicates, you have a Q0, Q1, Q2, Q3, Q4. And this different silicate species characterized by the degree of sharing of oxygen atoms between silicon atoms. So Q0 would be composed of isolated silicate tetrahedron, and this tetrahedra will be connected by cations like magnesium or calcium or others. And then Q1 would be one of the oxygen atoms is shared between two silicate tetrahedra. So this forms a chain. Q2 would be two of those oxygen atoms are shared, forming double chains. Q3 would be three oxygen atoms sharing, forming a sheet. And then Q4 would be a framework. So all of the oxygen atoms are shared. So here on the right is characteristic FTIR, Fourier transform infrared spectroscopy data, showing the absorbance, a function of wave number, and also showing the different peaks that we have observed and how we've indexed them to the different silicate species. So we can now look at a lot more of these curves for different magnesium silicon ratios, look at their intensities and the different peaks. So what we can see here is that there is a decrease in the Q3 and Q2 and an increase in Q1 with increasing magnesium to silicon ratio. So what this shows us is there's depolymerization of the silicate tetrahedral structure as we increase the magnesium silicon ratio, and also showing us the phase assemblage and the structure of the phase as we're changing the solution composition. We also looked at the microstructure of this phase, the morphology of this phase, using atomic force microscopy. And what is has revealed is that, so this is for a solution is 50 millimolars magnesium, 100 millimoles of silicon at room temperature. This is a 15-minute of reaction on the magnesium oxide substrate. What we can see is that the cementitious phases form as a densified film, which is about 1.5 microns thick, on the MgO surface. And then if we look closely, so if we zoom in, you can see this yellow and then this green. So even zooming even greater detail, we can see these nanoparticles that are about 100 nanometers in diameter. This is actually composing the film. We could also notice that the film is not completely filled in. So there are gaps, there are crack-like features. So these nanoparticles fuse, but they do not appear to completely fill this space. So this shows us we have this rapid precipitation of this phase, and then you have these colloidal aggregates that are stabilized transiently. And then we can watch this reaction happen over time. This is a 30 minutes, 60 minutes, 90 minutes, 120 minutes of reaction. We can see that this is the layer that we have observed from the 15-minute reaction from the previous slide is composed of these nanoparticles. But then at greater reaction times, you also observe the formation of larger particles that form and then coalesce to create another layer on top of that primary film. So these are these larger particles that are 2 to 5 microns in size. And this suggests that so as we increase the reaction time, the solution's supersaturation decreases. And this could be what is causing the creation of fewer nucleation sites. So we have larger grains at longer reaction times. And then zooming in into these one of these longer reaction time samples, we notice that the grain boundaries start to disappear. This could happen through a monomer by monomer growth or through recrystallization process. It also appears that the secondary film is more continuous than the primary film, which suggests that the primary film mediates further growth. But importantly, what this evidence shows us is that MSH grows by particle attachment, which is a non-classical pathway for precipitation. We also observed evidence for oriented growth and increased crystallinity. This is at higher temperatures. So we get these oriented attachment of particles. Sometimes you observe these more faceted grains that suggest a greater degree of crystallinity. And then if we use another substrate, for example, single crystal mica, we could observe this oriented attachment as well. This suggests a templating effect. So coming back to this idea of crystallization by particle attachment, this is a seminal work by Diorio and Science in 2015, showing that synthesizing the findings in the community in which we are increasingly finding evidence for this mechanism of crystallization by particle attachment, in which instead of a monomer by monomer addition, which is the classical mode of ions attaching to a growing nuclei, there are intermediate steps. So formation of nanocrystals or crystalline nanoparticles, amorphous nanoparticles or multi-ion complexes. And then these intermediate particles then form, for example, an oriented attachment, mesocrystal or nearly oriented and so on, that eventually evolves to form the bulk crystal. So I think this is significant because the nanoparticle architecture of the mesocrystals can then result in enhanced or novel properties. For example, by using this mechanism, we can combine high porosity with high crystallinity, for example, which could be useful for some technological applications. So we've shown, so far I've shown our work on the morphology of the phase and also the structure of MSH. So when we try to predict cement hydration and strength development, so what other data do we need besides those? In ordinary Portland cement, the cement I showed earlier, the hydration rate, which controls also the rate of strength development, is related to the rates of A-light, the C3S dissolution, and CSH precipitation. So if we'd like to predict the microstructure evolution and the phase assemblage evolution, we can do what we call a kinetic modeling. However, this requires knowledge of reaction rates, so both dissolution and precipitation. So in this context, the rates would be expressed as a function of their free energy. So this is a general rate equation that describes mineral dissolution and precipitation. And you can see this dependence on delta G, which in this case is the saturation state. So this treatment has been applied for CSH, for example. This is the growth rate of CSH as a function of beta. Beta here is an expression of the saturation state. So you can see as we increase the supersaturation and with respect to CSH, we get an increased growth rate as well. So we used small angle X-ray scattering to determine the rates of MSH precipitation. So we did these experiments at the advanced photon source, and we started with solutions with different concentrations of magnesium and silicon. And then we looked at the intensity of the scattered X-rays as a function of Q. So this tells us that we have an increased intensity, and also we have these peaks that are formed at certain values of Q that would be correlated to certain particle sizes as we increase the concentration. So we can take from this data, we can take the volume distribution of the precipitates, and we can take the integrated area under these volume distributions. And from that, we can derive a growth rate. So now we have an MSH growth rate. This is for the homogeneous growth of MSH as a function of the saturation ratio. We observe an increase in the growth rates with increasing saturation, as we'd expect from the model. This plot really, what it's doing is relating thermodynamics to kinetics, because the x-axis here, saturation, is related to thermodynamics. So now we know the rates associated with that thermodynamic parameter. Once we have these rate laws, we can input them in thermodynamic and microstructural models. This would allow us to predict the time-dependent solution composition, as well as the solid phase assemblage and the corresponding microstructure that would form. So it's also important to note here that the rate is time dependent because we have the evolving solution composition. That means like as you're growing, so you start at a higher saturation, and then you form MSH, that solution composition changes over time. So that means that the rate must also be changing over time. And that's something that would be incorporated in our kinetic models. We've also been interested in the structure and the mechanical properties of these MSH structures. So these are some of our latest works showing the acquisition of topography and elastic modulus maps using a technique called amplitude modulation, frequency modulation, AFM. So in AMFM, which is the technique we used, we have a cantilever that is oscillated its resonant frequency. That change in the amplitude gives us the topography image. This is the typical tapping mode that we're familiar with. And then we also oscillated a second resonance, and the shifts in the frequency tells us about the interaction between the tip and the sample. So this could be modeled to create elastic modulus map. So here on the top left, this is the topography image showing, so 0 here would be the substrate, and then the positive values of the precipitates form on top of that substrate. And then on the right, upper right, is the frequency distribution of the height. So we have the zeros corresponding to the mica, and then you have this positive values corresponding to the different heights for the precipitate. And then we have the elastic modulus map here in the bottom left, and the frequency distribution of the elastic modulus. But also for ease of demonstrating the different values, you could also look at the frequency distributions of the different subsets within this image. So you have the blue, the green, and the red. And this is showing, so by the way, so these elastic modulus maps are calibrated against the substrate, mica. The value for the elastic modulus of mica is obtained using nanoindentation. So we know that's 65 gigapascal. And then from that, we can derive the elastic modulus of MSH, which is depends on the morphology. So we have values of 54, values of 6, depending on where we are in our precipitate. We observe the small irregular grains and large faceted grains. And this is another example of these elastic modulus maps at different reaction times of 40 minutes of 48 hours of reaction. And we can see these bimodal distribution of elastic modulus that depends on the morphology. So either about 10 or about 57 gigapascal, depending on where we are. And also, taking this together, so now we looked at the different magnesium silicon ratios of 0.5 to 2. And you can see that for large and faceted grains, you have values about 40. For small irregular grains, you have values of about 5 to 15. And then we can also compare this with elastic modulus of CSH, obtained from, for example, from nanoindentation. We can see that the CSH has intermediate values between these two. We also observe a slight decrease in elastic modulus for small irregular grains as we increase the magnesium silicon ratio. This is something that has been observed as CSH has been thought to arise from the decreasing degree of polymerization with increasing magnesium silicon ratio. So the final piece of this talk is about degradation and degradation as a dissolution reaction. So if precipitation forms the cement phases, then dissolution of the hydrated cement phases, in this case CSH, would cause alterations in the microstructure, for example, increased porosity, which could lead to degradation of the concrete. So while solubility tells us about long-term behavior, it's really the dissolution kinetics or the rate of the dissolution that reveals the progression of this degradation. So this is showing some previous work on CSH dissolution as a function of the delta G. And we can see here that just like for the precipitation rate, the dissolution rate of CSH also depends on the Gibbs free energy. So the more undersaturated we are, the larger this delta G is, the greater the dissolution rate is. So we also quantified this dissolution rate of MSH. And what we did is to do time series in situ AFM images as we're dissolving this MSH that we grew on mica to dissolve, to obtain the dissolution rates. So what we use here, we have an environmental AFM where we have this fluid cell. This is the tip, and we have a sample. And the fluid cell has liquid exchange ports, then is sealed. It also has gas exchange ports. And what we can do is that we can image the sample surface as it's immersed in a reaction solution. Now, this is the 0 minutes of reaction, so the initial surface, 15 minutes, 30 minutes, 62 minutes, 92 minutes, 122 minutes. And this is showing a representative progression of the solution as we're observing them in the AFM. So we can then, looking at the bottom left, we could look at the average height in each of these images as a function of time. And then the slope, then we can normalize to the molar volume to determine a dissolution rate. We could also look at, for example, two images, this different reaction time at the same area. For example, at 0 minute, 122 minutes, we can take the difference between these two images to get a rate map. So with this rate map, the advantage is that it tells us about the spatial dependence of dissolution rate. So it tells us which morphologies dissolve faster. And we observe is that there's a greater dissolution along edges and along the smaller particles, which would be consistent with the presence of more reactive sites along those grains. So we take all these data together, looking at different magnesium silicon ratios. And what we've observed is that dissolution of MSH is faster than crystalline magnesium silicates. So these are the Tolkien lizardites. The lizardite is a type of serpentine I showed earlier. We can see it's faster, which is what you'd expect because of the presence of very large amounts of defects in the solids. I also added here brucite, the dissolution rate of brucite, the dissolution rate of amorphous silica, as well as forsterite. So forsterite is an isolated silica tetrahedral structure, Mg2SiO4. So we could see it's almost similar to the dissolution rate of that phase. What we've observed here, very interesting, is that these oriented particles dissolve faster than the non-oriented MSH. So this is something could be evidence for dissolution by particle detachment. So there's a paper that came out this last year. It's talking about this dissolution by particle detachment, which is the analogous, the inverse of that crystallization by particle attachment. So, but with this mechanism, we can get a much higher dissolution rate than if you're dissolving a bulk crystal. So I'll stop there. So today I showed our studies, ongoing studies, and the really recent studies talking about MSH growth, dissolution, and mechanical properties. We've shown that during growth, MSH depolymerizes with increasing magnesium silicon ratios. We've observed that MSH nanoparticles fuse to form 3D microparticles in 2D film, and that shows the structural hierarchy in MSH at both the nanoscale and mesoscale. And we'd really like to point out this complexity of mineral precipitation. I think this complexity, even though it's complex, it can be advantageous in exerting significant control over property evolution. So for example, we've observed the effect of morphology on elastic modulus, or the effect of orientation of these particles on the dissolution rate. So taken together, all of these studies provide insights into the cementitious character of MSH, showing whether this is something that could be a viable substitute for the typical cement that we use today. So I'll be happy to take any questions, and thank you so much.
Thank you so much, Erica. This is a fantastic talk. A couple of things, just housekeeping and announcements. The first one is the Acer Cements Division's abstracts have been extended to April 15th. So everybody has some time to submit those abstracts on the website. The second announcement is that if you have any questions, please put them in the questions and answers button down below. And I'll read those out to Dr. Erica LaPlante and make sure that those are answered. All right. So while everybody's typing up questions, I'll start us off. Erica, that was a fantastic discussion on all your latest results, and it's fascinating that this dissolution rate that you have just mentioned. Can you talk to us a little bit about maybe the pH dependence on those dissolution rates, and perhaps that initial solution that you talked about, a little bit more about the aqueous chemistry of that solution?
Yeah, so for these dissolution rate experiments, we dissolve them in water, and it's air equilibrated water. So pH 5.6. It's just deionized water that's been exposed to air. And we did its experiments under far from equilibrium conditions. And so we flow the solution through in the fluid cell. We stop the flow and then watch the reaction as it's happening. So it's also, we call it pre-drift experiment, but at the same time, it's far from equilibrium.
That's fantastic. Very, very cool results. All right, so I do see a couple of questions here. So from Anna Trindade, very incredible presentation. Thank you very much. Is the MSH rate of strength development similar to CSH, or is it actually slower?
There are studies that show comparable strength development with MSH and CSH. In our group, we have started actually creating mortars to answer specifically this question. So we're trying to approach this problem from the bottom up now that we know about the growth rates and the morphologies. So we're going to apply this knowledge as we scale it up and look at the rate of strength development. So that's definitely an important question.
Yeah, I would agree. And Erica, can you talk to us a little bit about maybe those curing conditions and the mortars that you're creating?
We are following, I don't know actually off the top of my head, but we're following some of the previous literature on MSH precipitation, as well as on some CSH mortars.
Yeah, very nice. Okay. All right, great. We have a lot of questions, so this is fantastic. All right, so from an application perspective, how do you envision, I know we're moving forward to a couple of years from now, but how do you envision this type of cement working in the field? What are some of the challenges that we really need to get done in terms of workability, curing time, and so forth to really be applied in the field?
I think so for MSH, and it's also true for magnesium-based cements, it's generally thought to not be suitable for rebar applications, for example, because of the lower pH. It's also important to think about where we're getting the reactive sources of magnesium and silicon. So in all of the studies that I showed today, I'm using solubilized magnesium and silicon. So we're not starting from a magnesium silicate or a magnesium oxide. I think there's a significant opportunity there, because if we can activate, right? So I think that's the word that we like to use. If we activate these magnesium silicates, there's a lot of magnesium silicates that would be fantastic opportunity for these types of cements.
Yeah, absolutely. Um, and there's some infrastructure applications, right, that would benefit from that lower pH. And I know we have looked at magnesium-based cements for infrastructure related to the nuclear waste disposal.
Yeah, that's true. Yeah,
So,
that's right.
so
Yeah, I'm
that's
glad you
that's
pointed that
fantastic,
out. Yeah. Yeah, and like CO2 injection well. So things that are, because we also think that this MSH cements would be also more resistant to CO2 attack.
right? That's fantastic. All right, moving on to some of the other questions here. So this is one from Ravesh. What implication does this work have on the selection of set time additives?
It's a very interesting question. We are investigating the effects of additives on the formation of of the phase. So there are two things. So because it appears, right? So we have evidence that show the MSH forms by crystallization by particle attachment. So that means that we can affect the precipitation through either the first stage of the precipitation, the formation of the nanoparticles, or the aggregation of the nanoparticles themselves, which I think is a really interesting question, right? So if you have an additive that controls the formation of the nanoparticles versus the aggregation of those nanoparticles, they could have very different effects on the final microstructure. So yeah.
Right, right.
Very
And that
interesting.
is a very hot research topic right now. So that's fantastic. Moving on to another question here from Yi Xian. Thank you for the talk. What is the reason behind selecting mica as the substrate for growing MSH?
Mica is very inert, so it's highly unreactive with water. So especially for our dissolution experiments, that's very valuable because it dissolves several orders of magnitude lower than MSH. That means that when we do our experiments, we can use it as a reference substrate that we know the height of mica is not changing, and we can align all of our images in the Z direction and the height direction so that we can get absolute heights for the precipitate. And also it turns out, so mica is also a phyllosilicate. It is similar to MSH structure. So when we look at the elastic modulus, that means that it would have a similar interaction between the tip with the mica and the tip and the MSH. So that also increases the robustness of our measurements in the elastic modulus.
Yeah, that's fantastic. Such an interesting approach. It's fantastic. Moving on to some other questions here. Well, this one is not based on research that you just presented, but I think it's really interesting for our younger viewership here. Erica, how did you get into this kind of research? What piqued your interest and what is your favorite part about it?
So I'm a geochemist by training, and I do this. So when I was like, thinking about the vision for the lab, I mean, as a starting assistant professor, like looking at the gaps in the field, and I saw this opportunity for MSH. I also saw MSH as a really good model system. So as a geochemist, we operate on model systems to understand concepts on the crystallization or dissolution, whatever, absorption, like different phenomena that occurs in mineral fluid interfaces. And MSH is a great model system. It's challenging, but the knowledge that we get from MSH, we can apply to other magnesium-based cements, which is also less explored. And also because of its similarity with CSH, we could also apply it to CSH, which is what we use today, which is always going to be important. And so it's challenging because it's difficult to characterize. So I think it makes us like be creative on the different approaches that we use to understand this material.
Yeah, fantastic. Okay, moving back again to research questions. Um, in the field, I have used magnesium phosphate cements. This is the question. Um, and these magnesium phosphate cements are really great for chemical resistance, and they have fast set and good compressive strength. So this question is curious about how maybe MSH compares to magnesium phosphate cements being used in the field in regards to maybe chemical resistance or even the strength.
I'm not aware of comparison. We have not done work on the actual mortars and concrete, and this is actually we are working on that now. But I think ultimately, think to the point of the question, like ultimately what we care about is the performance of this material at the macro scale. So thank you for the question. But I don't know the answer right now.
Right, right, yeah. Um, very different systems, and I think one thing that I can add to that is magnesium phosphate cements set really fast, mainly used for repair work, and so the compressive strengths tend to be higher since MSH sets a little bit slower. But there's something that we can, going back to that first question, something that we can definitely engineer with maybe some additives and that we were discussing. So that's very exciting opportunities there. Okay, moving on. Sorry, I'm not getting to all the questions here, but thank you everybody for sending those. Okay. Okay, once you determine the rate of dissolution, what options are there to decrease the time for this dissolution, for this rate of dissolution? So how can we maybe slow down this rate of dissolution? Has your research come up with any strategies for that, or is that still in development?
So the idea is so we have seen, for example, that the dissolution rate is controlled by the arrangement of the nanoparticles. So to decrease the dissolution rate, I think we can go back to how we are synthesizing the MSH and controlling the microstructure and maybe controlling the both the morphology, the microstructure, the chemical structure of the phase. And that's how we can change the dissolution rate.
Right. Oh, fantastic. Okay, we'll do one more question. And this one is a little bit more open-ended. But what do you think are the opportunities for MSH to be an achievable solution in terms of durability and decarbonization of our infrastructure?
I think that that's really the motivation for this work is as the hypothesis that it has an increased durability compared to CSH and also has a lower CO2 emissions if we're using different natural resources to create this phase. I think the question now is, would it really work? So is this cement really cementitious? And this is why we're doing all these studies, is to understand the cementitious character of MSH and how we can optimize the macro scale properties by looking at the formation of these phases, like right at the atomic scale, the mesoscale, the nanoscale.
Yeah, I couldn't agree more. All right, well, that is it and everything for our webinar series today. Thank you everybody so much for joining. Thank you so much, Dr. Erica LaPlante, for giving us this fantastic research presentation. We will be sending out announcements for when Dr. Kinsey Skilling can join us next time. But until then, we hope to see you all again soon. Right?
Thank you so much, everyone.
Thank you.
Thank you. Bye.
Bye.